Good afternoon, everyone. My name's Tim Rastall. I'm the Chief Technical Officer at Enspec Power. Today I'm going to talk about how we can use point-on-wave switching with gang-operated circuit breakers to alleviate a few grid connection issues that we're currently seeing. So just to give you a brief agenda of what we're going to cover, I'm going to start by discussing Enspec as a company, what we do, what the products we have to offer. The key understandings around this topic, so what's driving these grid connection issues that we're seeing, why moving to renewable generation is causing these types of issues. Then going to move into a viable solution, which is point-on-wave switching, the focus of this talk, how it works and how it can be used with gang-operated circuit breakers. We're then going to move on to a number of actual real-life applications. We've got 3 case studies that Enspec have been involved in for different types of grid connection issue and how point-on-wave switching help to alleviate those problems. And then we're going to conclude with any questions that you may have on the topic. So to start off with, about Enspec. So Enspec are a privately owned electrical engineering company. We've been operating in the renewable space for many years. We're a full service grid connection and power quality service provider. So that means we take the customer through the whole journey. From the very beginning, if we look at a wind farm, if you design a wind farm, you need to start by checking it against grid connection and power quality grid codes. So we will build models in various different power system softwares. We'll run simulations and we'll check if that site is compliant against various different grid code standards. From there, you move into our actual product range. So if you do come across a grid connection issue, that could be a P28 voltage dip non-compliance, which is the main topic here, or a G55 harmonic non-compliance. We have the expertise to design, manufacture, supply, and commission solutions to those problems. So these sites can be grid code compliant. So these are the various kind of departments within Enspec. You've got your power system studies and power quality surveys, and then your actual manufacturing product delivery areas, harmonic filtration, reactive compensation, point-on-wave switching, and power factor correction. And then we have a team of on-site services, so we can do maintenance, site surveys, and things like that. We work with a variety of customers. That can be from the renewable developer themselves. So, for example, EDF Renewables, who are building a wind farm, building a battery energy storage plant. Also, the balance of plant contractors, those that are tasked to actually pull together the projects and build the sites. They sometimes are responsible for grid code compliance. And then also working with network operators, Scottish Power Renewables, SSE. One of the case studies you'll see is the application of point-on-wave switching for the grid operator rather than for the customer. We have global expertise and experience. We've got equipment in all continents across the globe, and we do consult worldwide. However, we primarily focus currently on the UK market and the renewable journey of the UK. So some key understandings about why this is an issue and why point-on-wave switching can help. So traditionally, our generation was large, thermal, rotating, spinning assets, and they were located at the central areas of our network. There we had strong transmission networks, strong assets, and then they got gradually smaller and weaker towards the edges as we distributed that power to homes and businesses. This has now been completely flipped on its head, because if you think about it, where all of the natural resources are for wind, solar, they're not located centrally to the UK. They're more likely on the edges. So we're now trying to connect multi-megawatt, gigawatt wind farms and solar farms at these very weak areas of network. And we're trying to then transmit that power all back into the center where the network's just not made to do that. So these are the kind of issues we're coming across. There's a mismatch in the network strength and stability and the size of the asset that we're actually trying to connect to that network, which causes these types of grid connection issues. So like if you were to look at a wind farm, for example, you have your grid connection, and then you have a whole array of cables. You have big transformers to take that grid connection voltage, could be 33 kV, 132 kV, and transmit it down to lower voltages of the turbines. You have to energize that site. So you've got this weak network with a weak asset, with massive wind farm assets and transformers and cables. You're trying to energize them. They're creating transients, inrush currents, and the stability and grid strength is just not there to support these large assets. So what's the solution? One viable solution is the use of point-on-wave switching. To kind of give you an overview of point-on-wave switching, this is a typical relay, as it would look. It's an electronic device, and it effectively becomes a middleman between your close and open controls for your circuit breakers. These circuit breakers could be controlling transformers, cables, and it becomes a middleman between those controls and the circuit breaker to control the precise moment that that circuit breaker closes and we have electrical conduction to within 1 millisecond. Now, why is this important? How can this be utilized? Now, one of the common problems we have is energizing transformers on these weak networks. Now, a transformer is used to take a voltage from one level to another level. When the transformer is energized and there's not much load on it, it's not really doing much. It's a steady state. The issue we have with transformers is when they're off and we want to turn them on for the first time, or if they've tripped, for example. Now, there's a phenomenon known as inrush current. So if you have a transformer, it's sitting there off and you turn it on. If you cause the transformer core to go into what we call saturation, the transformer will draw a very large amount of current for a very short amount of time. It'll have a very big peak. Now, this inrush current will cause the grid voltage to collapse. And in the UK, we have standards and regulations to say how much you can collapse the grid. And that's because it leads to things like lights flickering, disturbance on other people's loads, and general instability in the grid. This is what it looks like. So the graph on the bottom, that's a typical inrush current trace of a transformer that's just been energized. So as you can see, it goes from zero current to a very high peak, and it then decays down. That's all done in around a second, which you'd think is not a problem. But as you can see, the top graph, that is the voltage at the connection point that we've just energized that transformer on. Effectively, 1 per unit is like the ideal voltage that we're looking for. And as you can see, it causes a massive collapse in the voltage, which then recovers. Now, that massive collapse, if you were to imagine we just let that go unchecked and we were creating these voltage collapses all over the network whenever we switched to transformer, we'd have a very bad, poor quality supply. We'd have flickering, we'd have loads tripping, we'd have loads damaging. And effectively, if we completely left this unchecked, it would lead to massive grid instability and potential blackouts. So this is the common reason that we're interested, and it's a problem when we're energizing transformers in weak networks. So how does point-on-wave work? So as we just discussed there about transformer saturation, when you open a transformer, when you de-energize a transformer, there is a residual flux left in the transformer core. All this is, the transformer's a magnetic, electrical magnetic component. The core is magnetic and it has lots of kind of particles that rotate when the transformer is energized. When the transformer is de-energized, all of these particles stop rotating and they all point in one direction. That's the residual flux. It's the magnetic polarization of the core. Now, if we then energize that transformer at a different voltage point that doesn't match the residual flux inside that core, that's when we cause saturation and the transformer draws a large inrush current, and that's when we get this voltage collapse. Now, the VisiMax point-on-wave technology can watch the de-energization. It can calculate the residual flux in the transformer core, and it can then calculate the optimum closing angle for the circuit breaker so that we don't take the transformer into saturation. This is shown here as this interesting graphic. As you can see, every closing angle has an opening angle that would result in low inrush current. Effectively, the y-axis there is inrush current, and we're targeting these blue zones. So for every opening angle that you could possibly have between 0 and 360 degrees, there's an optimum closing angle. That's what the Syncrotex algorithm is doing, and that's how it's allowing us to alleviate these issues. The integration is pretty simple. You've got your transformer, you've got a number of VTs and CTs, you've got a synchronizing VT so it can see the phase angle of the grid and control when it's going to switch the circuit breaker, and then it's got a downstream PT, and that's what it's using to actually watch the transformer de-energization and calculate the residual flux. This is shown here quite well in this graphic. This is the voltage when the transformer was energized and at steady state. And at this point in the middle of the graph, this is when the circuit breaker has been opened and the transformer has been de-energized. you actually see the voltage has a slow collapse to zero. And then the residual flux, which was following the voltage, a differential pattern, 90 degrees displaced, also goes for a collapse. And then we have this steady state level. As you can see, the three straight lines, that's our residual flux. So that's the transformer de-energized, the synchrotech calculated that residual flux level. What it then does is it knows how long the circuit breaker takes to close. So for example, if you were to say close circuit breaker, it will take around 50 to 100 milliseconds for that circuit breaker to actually mechanically operate and electrically conduct. So we pre-program the synchrotech with that knowledge. It knows the residual flux. It knows where the grid is currently because it has that synchronizing VT. And all it is just a bit of a math equation where you say close and it waits until the target angle that it wants to hit is, say, 100 milliseconds ahead of this point, if that's the circuit breaker time, and then it sends the signal to the circuit breaker. So it's literally a middleman. It takes the signal and then passes it to the circuit breaker at the right point. And as you can see there, 0.4, that indicates the target angle that we're trying to hit. And that you can see there, that's when the current and the voltage has appeared and the circuit breaker is closed and energized the transformer at that point. So yeah, into a number of actual applications of this technology in action, what it does and how it alleviates the impacts. So number one, this was a large wind turbine project, Viking Wind Farm on the Shetland Islands. So it's a joint venture between SSE Renewables and Shetland's community. It was a 103 turbine wind park. Each turbine was 4.3 megawatts. And it's basically shown there to provide enough electricity for 475,000 homes and save 500,000 tons of CO2 per year. So it's going to be one of the largest operational onshore wind farms when it is commissioned and in service. Now, the issue is that if you think about a 443 megawatt wind farm on the Shetland Islands, the Shetland Islands' current network is not very big, it's not very strong. Now, there's a HVDC interconnect being built specifically for this wind farm. So that's going to take the electricity generated on the Shetland Islands and send it to mainland UK. Now, the problem is you can't assume that the HVDC interconnect is going to be on, working 100% of the time. Now, if you lose that HVDC interconnect, you cannot leave 103 turbines with no power on the Shetland Islands because there's wind, there's rain driving in, and turbines need to rotate their nacelle to point into the wind at all times. And they also need to keep their motors warm, the oil and the lubrication running. So they need power at all times. For this reason, the Viking Wind Farm has an extra connection to the Shetland's 33 kV network. The idea being that if the HVDC goes down, they can energize the site from the 33 kV and keep the turbines power and in preservation mode. Now, the problem is that the fault level on the Shetland Island is 46 MVA, and we're trying to connect 103 5.15 MVA cast resin transformers. Because there's 103, the P28 standard means we have to apply the frequent limit, which is the tightest voltage depression limit, because we've got frequent operations. We're going to have 103 of these grid disturbances back to back. So this gives you a little bit of an example of what it looks like without point-on waves. This is the inrush curve, just as we'd shown at the start, from a transformer energized without point-on wave. This is a real-life waveform from the site. When we arrive at site and our commissioning engineers start to program the relay, the first operation we have, there's no timing, there's no flux. So you get a random operation that looks like this. You can see there that you have that sharp initial inrush current, and then the bottom graph just there, that's the voltage. So as you can see, the minute we energize, the voltage has a massive collapse, which would obviously be way out of the P28 limits. This operation was actually done on a diesel generator mini grid package. So don't worry, it wasn't actually a P28 non-compliant operation. So we were doing that to do the commissioning, so all the turbines are ready to go onto the real DNO without causing these types of disturbances. Now, when you commission the point-on wave and you put the point-on wave in service, this is the type of result that you get. That's the exact same graph at the exact same scale, but this time with point-on wave switching. And we achieved around a 0.2 per unit inrush current, which is a massive reduction from the 4.5 that you get without point-on wave switching. And once again, the exact same graph, same scale. That's the voltage. You can see there's effectively no impact of switching the transformer. So this is the idea. We now use point-on-wave switching to switch every transformer, and this is the impact we have on the Shetland's 33 kV network each time, making full P28 compliance and not causing any disturbances on the network. Challenge 2. So this is looking at the technology and the challenge from a slightly different angle. So if you were to imagine we're moving to this renewable generation, it's intermittent sources, we're getting closer to our demand. We could have a scenario where we're desperately trying to avoid it, but we could have the scenario where we experience a blackout. Now, in that instance, we're then without power, the grid's de-energized, and we need to somehow get that network back online. Again, traditionally, we would have these large thermal generation assets at the center points of our network. They could power up, and they could become anchor generators, and they could restart the network from these central locations. Now, as we move to renewable generation, we're decommissioning these large assets, and we're moving to many distributed assets all around our network. So we need to find a way to ensure that we can black start our network from these types of assets. This was an initiative we looked at with National Grid and Scottish Power Energy Networks. It's called the Distributed Restart. Now, this was a world's first initiative, and the idea being they were looking at using an 11.6 MVA grid-forming capable battery energy storage system to actually re-energize large amounts of the Scottish Power transmission network from 33 kV. Now, again, your issue here is kind of flipped in reverse. This time you're trying to energize large assets, but from your small renewable generator. You have the exact same issues we've already discussed. You've got big transformers that are going to be drawing huge inrush currents. You've got big cables going to be drawing inrush currents. We need to find a way to lessen the impact of energizing those so this relatively small battery energy storage system can actually handle that. So this was the first test that we did, and this was without point-on-wave. So we just used the battery energy storage system to energize a 90 MVA grid transformer. So it was a 33 kV to 132 kV. And 10.6 kilometers of 132 kV overhead line. So it energized. You see the initial inrush current. You see the voltage go very unstable, and the BESS plant effectively tripped to protect the battery energy storage inverters because of the grid instability. So obviously that's not ideal. We've got this big blackout. We need to get critical power back on to hospitals, to businesses, to homes. We tried to do it, and it all kind of de-energizes again. So we need to have a solution in place that's reliable. So then we tried it with point-on-wave. So effectively, we've got the battery energy storage system. We've got a 33 kV circuit breaker that's now being controlled with point-on-wave to energize that 90 MVA grid transformer and the 132 kV overhead line. And as you can see, we massively reduce the initial inrush current. This means that the voltage instability is not seen anymore. The grid forming BESS is able to cope with this level of inrush current, and we get a sustained energization and successfully energize these large transmission assets from a very small anchor BESS. The idea then would be that we'd add further areas of network, we'd connect to a local solar farm, a local wind farm, and we'd build back the network from these renewable assets, all using point-on-wave to reduce the switching impact. And the idea was actually to take a full-scale network re-energization from estimated to be around 7 days to around 24 hours. So this would be a massive increase, and critical power applications would be back on within a few hours. So obviously saving kind of lives in some critical situations. Challenge number 3, this one's a little bit unique. It wasn't coming from the customer's renewable generation side, and it wasn't coming solely from the network side for a black start scenario. So SSEN, we're looking at initiatives here to help with distribution transformer losses. So what you have typically in a 33 kV distribution network is you'll have 2 parallel transformers, and they'll be feeding a town or a certain area of network at lower voltage. Now, obviously, at peak times in the morning and in the evening, we do need both of those transformers because of the power that's going through them. However, in the middle of the day, the load drops off massively, and you have these 2 large transformers both sitting there at relatively low loads. And that's not necessarily a problem unless you consider the offload losses that those transformers will have. They're effectively sitting there consuming electricity and wasting energy when they're not needed. Now, obviously, you could switch one off. The issue is If you switch that off, then you have to switch it back on, and you create these grid impacts. Now, the DNO, just like the customer, they have to maintain power quality. They have to comply with harmonics, P28. So they can't just go switching on and off a transformer just to kind of save the costs. So we looked at an initiative with SSEN. We would apply point-on-wave switching to a pair of distribution transformers. At a time of low load, one of those transformers would be switched out. Then when the load's coming back up, we'd switch that back in with point-on-wave, causing no impact to the network. And then that transformer will be there, but we've saved all the no-load losses in the meantime. Now, this is hopefully you can see this graph a bit small. This is a graph from October to December when the system was commissioned and in service. The green is one of the transformers, the blue is the other. So effectively, they just took it in turns, and one day switched one off, the other day they switched the other one off. And this is the peak inrush current that was seen for every energization. Now, these were nominal 15 MVA transformers with 262 amps per unit rated current. The inrush was maintained every single energization for a period of 2 months to less than 75 amps. So this would have not caused any impacts in terms of P28 harmonics on the customer's supply. And they saved lots of money in terms of the no-load losses. They estimated if they put this out over their network, it would result in millions of pounds of cost savings in terms of no-load losses, so a significant amount. That's effectively me and the different case studies and examples. Thank you very much.